Um, Thank you, Professor Krishna. Already, I'm very honored to be invited and to attend this webinar, not only as a attender, but only as a speaker. So thank you for organizing all these regular activities, which gives a lot of new knowledge, new insights into the ideas, and of course, connecting different fields of expertises. So Slovenia is calling. Secondly, I would like to say warm or give warm welcome also to all the attendances. Thank you for taking your time. So as stated today, I will be talking about coal ashes, their characterizations and or their characteristics, steps how to use this material as a CO₂ absorbent and how to use it in the geotechnical composites. So, of course, I will start with a brief fact that economy of the European Union is transitioning from linear to circular model. So aiming to maximize the life cycle of materials, products, and resources within the economy, and of course to minimize the generation of waste. Construction is ready to be a key sector to achieving those goals, but efficient overreaching strategy is needed. So industrial carbon management strategy on how to achieve homogeneous development of carbon capture and storage. The goal is to establish a single market for the CO₂ transport and the storage services through Europe by 2030. So to support carbon neutral industry and the emerging carbon removal industries through different technologies, such as carbon utilization, and carbon capture storage. As it's clear here, carbon capture and utilization, so storage, contributes in the larger scale to the net zero. So this is one thing that is very promising in order to achieve those goals. Another thing is by using the carbonation as a strategy, we somehow may open a new chains in the circular economy model. If we use cement, concrete, and aggregates, so the construction materials, and upstream the CO₂ sources through CO₂ conversion into the byproducts, this of course improves the circular economy and give added value to carbon capture. So somehow the ideal system for the mineral carbonization of coal ash is defined here in this picture. It is taken from the literature, which is assigned below. So the ideal system is to use fuel gases directly from their sources, to use relatively or low calcium fly ashes, which are supposed to be the ones that cannot be used like a supplementary cementitious materials. So the further step would be direct carbonation using either semi or even better regarding the effectiveness, the direct aqueous carbonization. In this way, the use of this material in construction products and earthworks was already somehow shown. At least there is a path, but we have to achieve it in larger degrees, in larger scales. So ashes, fly ashes, coal ashes, all ashes, like an industrial byproduct, are described as one of the most complex anthropogenic materials. It is described also that globally it is like the 5th largest raw material source. But we have to be aware that the term ash is somehow generic name because it incorporates all the different material which is produced during the incinerations using different processes, different input materials, different handling on the fields, on the landfills, different ways of transportation, etc. So not one material, they differ one from another in quite larger degree. We can name them according to the input material, which is combustion. So like a coal, ash, co-incineration, or either usually is used like also the term by the procedure during which it is collected. For example, electrophoretic ash, cyclone ashes, bottom ashes, and so on. The thing is, we have to be aware that those materials, even though they have the same name, can differ one to another in a quite large degree. So regarding the using of fossil fuels, yeah, it is a fact that we are trying to avoid as much as possible, and there is a strong strategy to try to reduce it or also not use it at all. But ashes definitely will be the material, the waste byproduct that will be increased in the quantities even in the future. Here is just one example regarding the incineration of solid waste, fluid waste that, for example, because of the climate changes and the following catastrophe flood events produces also like huge quantities. Like here is an example from Belgium in September, where 90,000 tons of domestic debris were collected by 8 kilometers through the highways. So 60% of those debris were recycled, but the rest of it was incinerated. Again, Germany, flood. This is the thing that will be the quantities of this material is going to be higher and higher in the future. So if we go one step back, there are already some technical specifications and standards which are defining how the specific ash should be or could be used, and what this ash, what are the specifics of those ashes that can be used for specific applications. This is especially very well done for supplementary cementitious materials, for road structures, also the earthworks and different technical specifications. But the thing is that they usually are describing the coal ash, but with the really rare exceptions, the usage of other types of ashes are not really defined, at least not as deep as those described here. But there were some analytical procedures and steps done which proved that this material can be valuable if it is used at the right way, so by using the right steps and to use it for the right applications, of course. So the aim of today's webinar is somehow to speak about different ashes from coal combustion, their characterization, the characterization of their hydraulic properties, which is a very important characteristics. The third step, a research of carbonation efficiency, and at the end, some perspectives or some results on the geotechnical properties of the composites prepared from those materials. So 5 different ashes were used, 4 of them from Slovenia and 1 of them it was from the neighboring country. So FA1 was collected fresh, so directly from the production. FA1 pond was collected from the landfill. FA2 was collected from the summer regime, FA2 winter from the winter regime, and FA3 it is collected from the neighboring countries. Although they are all specified as the fly ashes, FA2 samples are basically a co-combustion samples because they are during the incineration, they are using some wood chips, and the quantity of wood chips used is larger in the winter because they are increasing the calorific values. So here in the first line, you can see the visualization, and here more deeper insights into their microstructure appearance. There are different colors, of course, because they also, what moist content is different. They are also, again in FA2 samples, it is basically not purely fly ash, but 9% of the bulk volume is composed of the bottom ash, because this is like standard procedure during the collection after the producing. The first thing was characterizing the physical properties, so particle size distribution. It's quite obvious that if we compare the fresh and the pond one, so the green and the purple one, the ash collected from the pond is larger grained, and also the winter in comparison to the summer regime, FA2, is somehow larger particle sized because more wood chips is used. The most narrowest particle size distributions show FA3. Then we specified also some other physical properties, such as loss on ignition, grain density, and specific surface. What is the most obvious in the loss of ignition is the fact that in the case of FA2 ashes, the quantity of the loss on ignition is relatively high in comparison to the other 2 materials, ashes. And we know the reason. It is they're using wood chips, of course. Grain density doesn't diverse between different samples, really, but specific surface also shows the highest values for the FA2 ashes, which we will see also later, or we can see it also here. It's shown in the microstructural features from the microscopy. They contain different leftovers from the combustion of organic material. One step further, we checked the pH and conductivity of the leachates of those ashes, and the pH is relatively high again in the FA2 ones, while the conductivity is the highest in the FA3. Bulk chemical composition performed by XRF showed that our investigated ashes are located here in this triangle. This triangle is from the article from Snelling's Feature and Emerging Supplementary Cementitious Materials. But the thing is, those ranges, you can see here is the location of calcareous coal fly ashes and siliceous fly ashes. Our ashes showed a bit different chemical composition, especially FA2 are moved more toward more alkalic elements. So the first one, Fa1, Fa2, and Fa3 are somehow more siliceous, or at least aluminum ferrous in those directions. Next step was detailed detailed mineralogical or phase composition. We know that at least coal ashes are composed of quite large fraction of amorphous material. Amorphous phase is the phase which I can say is guilty for the pozzolanic, or let me say latent hydraulic activity, but of course also the composition of amorphous phases differs one between each other. But anyhow, the overall, the largest quantity of the amorphous material in investigated ashes is in the Fa1 ashes, so in the fresh and in the pond one, while in the Fa2, so from summer and the winter regime, this quantity is quite, let's say, smaller. Fa3 is somewhere between the Fa1 and Fa2. The other thing is the presence of quartz, which is inert mineral phase, if we are talking about the pozzolanic latent hydraulic activity, is the most evident in Fa3, while in Fa1 its quantity is relatively small. We have like some common mineral phases which are present in all 5 of them, such as ferrous oxide, spinels, or hematite, and some solid solution mineral phases from the family of feldspar group and melilite group. So the mineral phases from melilite group are described to show a weak hydraulic property. And here we have in Fa2 winter regime, we have also 8% of mineral phase brown millerite, which is a well-known hydraulic active mineral phase. It is present also in the cement clinker. Also, we can find in this material some phases which shows that material reacted already, probably to the because of the contact with the air moisture. Here in Fa3, for example, ettringite was already formed. And besides that, like there are also phases like carbonates, calcites, which can be the product of the reaction of the primary material, which was really fresh and it already converted, or it was like a primary phase in the material itself. Okay. Sorry, something is jumping. So now at this step, we are aware that there are some phases that could potentially react only with water. So we tried to define latent hydraulic activity of those ashes, meaning adding the material, mixing the material only with water without any additional additive, which would increase this reaction. So we made pastes with each ash, and we made those pastes with two different water to ash ratios. The first one, it was 1:1, and the other one was 2:1. So the lighter colored lines present the pastes with ratio 1:1, and the darker one with ratio 2:1. So for the ashes Fa1, one fresh and pond, we can see that the reaction, the heat release can be detected relatively soon after after the mixing it with the water. On account, when larger quantity of water is added, this does not happen. In comparison to Fa1 fresh, Fa1 pond material does not show any heat release, meaning nothing is happening regarding the hydraulic reactivity. Fa2, in both cases, in summer and winter regime, we can see the heat release, again, in a relatively early ages of hydration. But in the case of Fa2 winter, the quantity of released heat is higher in both cases, when 1:1 and also when 2:1 water to ash was used. If we go further, Fa3 ash, again, similar like Fa1 pond, doesn't show any heat release. So what could be the reason for this? Fa1 pond was put into the environmental with natural environment. So it was in contact with water, in contact with different materials. So if it primarily included some reactive phases, those phases probably will already hydrated. So everything that has left is something that is, let me say, inert in the way of reaction hydraulic reactivity. Fa3, it seems, besides of mineralogy, which we were interpreting a bit earlier, also showed that nothing is happening. So it probably should have some additional material which would increase the reactivity, but with water, it doesn't react. So those three ones are the one that shows, but it seems that Fa2 winter ash reacts with the water in the highest degree. One step further then was to check the mineralogy of those pastes. We choose the Fa1 fresh one because we saw that the pond one didn't react. We use the Fa2 winter because the heat release, the degree of heat release was the highest. And for like reference, check also Fa3 because nothing was happening there. So we checked the composition of pastes with the ratio of water to ash 1:1 during different time intervals, so 27 till 980 days. Here clearly you can see that some hydration projects were formed during the increase of time interval. In the first case, ettringite and monocarbolaluminite. In the Fa2 winter, which showed the largest heat release, also the ettringite is formed, hydrocaluminite, and also in a smaller degree, monocarbolaluminate. Those are all the so-called AFM phases, which represents the typical hydration products of cement hydration. In Fa3 case, okay, something little happening, but in general, nothing is happening, which is confirming the isothermal calorimetry results, which we were looking in one slide before. Also, the relative intensity of hydration products formed are the highest in the Fa2 winter, which again confirm or support the results from the heat release. Those hydration products can be easily or nicely seen also on the surface of those pastes. So electron microscopy showed the presence of needle-like ettringite type of hydration products. Also, the EDS confirmed the appearance of this ettringite phase. And on the other hand, again, also we confirmed the presence of calcium aluminates, like platy ones, which I was talking about, representing the hemicarboaluminates and monocarboaluminates. Till now, we tried just to check either the material reacts with water or not, those samples. But at the further steps, we tried to use also the procedures that are prescribed in different standards. But for the hydraulic activity, only the standards for only the standard for cementitious materials is prescribed. So we said we will try to check also this, but we have to have in mind that those systems are completely the same, because you are exchanging 20%, 25% of fly ash with the cement in order to prepare a mortar, standard mortar bars. But anyhow, the results gave us some clue about how could material react if we would use the water and put additional activator inside, such as cement or pure lime, in order to increase the pH and increase the solubility of the amorphous phase. We can see that Fa ashes resulted in quite good results. This green line are the limiting values measured after 28 and 90 days. You're measuring the strength of those mortars, and those are results of relative comparison to the references. In the cementitious systems, it seems that the most promising ash, which was so-called most promising till now, not in the cementitious systems, AF2 winter, here is showing the lowest characteristics, and Fa3 again is the one which is basically the most promising for the cementitious systems, because after 90 days it reaches the limiting values. Another prescribed, let me say so, procedure for analyzing the hydraulic activity is again connected with the supplementary cementitious materials. You're measuring heat evolution by isothermal calorimetry, and it is so-called R3 test, which was prescribed by Rylam, according to ASTM C1897. So here you are measuring the heat of hydration in a mix of different chemicals, where you are adding your material of interest. And here the characteristics of Fa3 ash, which was shown to be promising in the measuring of the strength values, here shows even greater potential. Some rough assessments are that heat of hydration for ashes is around 160 and 300, between 160 and 360, and Fa3 totally totally fits into those limiting values, while the rest of them are below, or at least after 7 days, plus and minus fits into this prescribed range. But we decided to go further with the Fa2 winter ash. Why so? I already highlighted that it didn't show really good potential in the cementitious systems, but it showed very promising features when it's used in the combination with water. So combination with water is used usually in geotechnical applications. Of course, if there is no need for further stabilization or increasing the strength. So that's why we move on with further defining further characteristics on this ash. We can see that free lime content, according to the assist-N parameters, is quite high. It's too high than prescribed for the usage for the cementitious composites, and it includes also quite high quantity of reactive calcium oxide, which is on another hand very promising also for the carbonatization processes. Of course, one very important thing when you decide to use or try to check either some industrial byproduct material can be used or cannot be used is environmental impact. So we performed the leaching test according to Slovenian legislation for Fa2 winter S, which was chosen for further investigation. And the results showed that concentrations of barium and fluorine exceeded the limiting values. Further step was to prepare the geotechnical composite according to the standard Proctor compaction test and perform the leaching test on the composite, which was prepared from original ash. So the results showed that the concentrations of barium and fluorine, which were exceeding the limiting values in the raw material, in the raw ash, here were defined below the limit. So the thing is that definitely different, we can assign this to different facts, such as hydraulic activity of ash and, of course, lower permeability of the material when we are checking the Proctor, the material prepared by Proctor compaction procedure. So further, we took steps to define the characteristics of this ash in incorporating or in sequestration of CO₂. We used 3 different exposure conditions. So like first one was a vacuum bag, like a reference. And the second one was chamber for dry carbonation. So air moisture was only 50%. And the third one was chosen according to the higher moisture content and lower CO₂ content, just to check what influences more, either higher content of CO₂ or higher content of air moisture. And the different exposure times were used. The results show that, of course, curing chamber with high moisture content was the most efficient during the carbonation of the material. We can see the depletion of lime, while the calcite, the quantity of calcite was increased, and also the quantity of portlandite was decreased. And on the other hand, some hydration product also formed, which is the reason of the contact with the moisture, as we already showed before. So when we defined or proved that the water content is very important parameter in order to increase the carbonation process, we take a further step of investigation of carbonation mechanism by adding different quantity of water to the ash and use the chamber conditions with a 50% of relative humidity and high degree of CO₂ concentration. And at the first step, we took short time intervals, so like half an hour till 24 hours. It was very obvious that increase in mass happened after the carbonation, and this increase was the highest for the sample in which the quantity of water was the highest. So the 40% of water which was added to the material was reflected to the higher increase in the mass. The other thing, particle size distribution, also showed that the higher quantity of water was added, the let me say so, the distribution moved to the right, which means that the particles of the ash carbonated was larger in comparison to only 10% or 20% of moisture added. And of course, the larger grains were measured at also larger time intervals. Next further step was searching for the results of pH and the conductivity of those different carbonated ashes, different carbonated ash or ash carbonated by mixing it with a different quantity of water. And it's quite obvious that pH lowered with the content of added water. Again, for 40% of addition of water, the pH showed the smallest values. The same, the parallel, somehow similar trend was shown in the case of measuring the conductivity. On the other hand, we tried to check further the concentrations of silicon and alumina, which are the phases that are, how to describe, which are guilty for the mineralization of hydration products from the pozzolanic or latent hydraulic material. So silicon showed the different trend than pH, just the opposite, because of the concentration of silicon was the highest in the case when the highest moisture content was used, which shows to at least partial pozzolanic, or let me say hydraulic activity of this ash. So the solution of particle which are called like then pozzolanic reaction, and ensuring to be more silicon present in the pore solution, from which then hydraulic material can crystallize. The concentrations of calcium showed the opposite results than the silicon, but this is of course connected with the carbonation reaction. Less calcium in 40% addition of water means higher degree of carbonation. Probably some calcium accounted also for the mineralization of hydration products, but this trend is very obvious. The results further confirmed the highest quantity of carbonates, calcium carbonate, present in the sample with the highest water content. This was confirmed by using the DT-TGA methods, which is quite obvious here in the graph and also in here with the right figure. XRD, so phase composition, also nicely showed that in the case of samples with a 40%, the highest percent of moisture content, the calcite, this is the most intense peak of calcite, is the highest, so the quantity is the highest. While in the other side, of course, calcite was formed on account of the lime presence and portlandite presence. And we can clearly see that the concentration of lime is decreasing with the time and also with the water content. Some microscopy features trying to define the mechanism of carbonation. Here we can see that this is, according to the microstructure, a bit different, smaller differences can be observed, and also the EDS results show so. So interesting was that we try according to the ratio of oxygen and calcium, then define either it is in the form of carbonate or in the form of portlandite, or at least in the form of lime. We can see here this part of the particle is formed from the calcite, while this is like in the middle stage of portlandite, which will with the time and in the combination of CO₂ from the chamber or air, then crystallize and transverse to the calcite. Here again, we can see like, I will say, interstitial transition zone between the outside and the grain itself. And it shows that this part is still a lime, while this inner part has already carbonated to the calcium carbonate, to the calcite. Microscopy also shows some smaller other details, like how the changes in microstructure during the carbonations were conducted, and also give us an answer on a question: why can be a small amount of lime also present in the samples at the largest time interval and highest water content? And here it is proven that some of lime or portlandite is embedded in larger grains. And when you prepare the samples for XRD, of course, you pulverize it and you give you release those parts which are embedded in larger grains, and that's why we were keep getting at least some of lime in our material, and this resolves our puzzle. Further step was comparison of heat of hydration from the fresh and the one that was the most successfully carbonated. And again, we see the delayed reaction. This is proof that it incorporates at least less lime, less portlandite, and also less some other potentially hydraulic materials or phases. That's why, but still, it does react, at least to a small degree, but it does. So the somehow idea was, if we see this here, probably if this material will be used for Proctor compaction tests, so for the preparation of geotechnical composites, we will still have some beneficial of its hydraulic property. So this can only be a positive characteristics. So this was also the reason to take another further steps, which was somehow defined to check the longer time periods and to use the carbonated sample of ash for the preparation of geotechnical composites, and then to follow the mineralogy of those geotechnical composites. We again use CO₂ chamber and humidity chamber with higher moisture content and lower in the combination high water content, lower CO₂ concentration, and CO₂ chamber just the opposites, and duration of exposure was 7 days. So here is the comparison of fresh ash as it was collected after humidity chamber, where it was kept 7 days, and CO₂ chamber where it was kept also 7 days. It can be clearly seen that in the case of the humidity chamber, some hydration products were formed, like ettringite. In original fresh ash, it was not present. Here it was. You can also detect the peaks from AFM phases, which also represents the hydration product. We can clearly see the increase in the peak of the calcium carbonate, so of the calcite, and the depletion of lime. Here, the peak is smaller than in the original one. In the contrast, in a CO₂ chamber, practically nothing much is happening because of the lack of the content of the water content, which was shown earlier in the beginning of the presentation, and this is another confirmation also at the longer time period, so after 7 days. Further, we made a Proctor composite from this ash, which was aged 7 days in different chambers, and then we checked the different time intervals of composites after 2 days and 30 days. In the humidity chamber, again, we can see the formation of different hydration products in the Proctor composites after 30 days. So this material is still at least a part active, but it already sequestered some CO₂, so we have two benefits. On the other hand, when checking CO₂ chambers, so lower relative humidity concentrations, again, nothing much is happening also in the Proctor composite itself, and the results are practically the same as when we were identifying the raw material itself, the ash itself. So some geotechnical parameters were also defined when using fresh and carbonated ash. There are some differences, and maybe the largest differences are in unconfined compressive strength, where the fresh ash achieved 5.5 megapascals, while carbonated only 0.8. But somehow the the natural materials for embankments, their unconfined strength is like 0.1 to 0.2 till 1 to 1 megapascals. So this is not even such bad result. As I'm not like a primary person who is dealing with such geotechnical parameters, I will just conclude with not go into the details. If there will be some question, I will be happy to answer them after the discussion with my colleague. But anyhow, the application of the CO₂ treated ash shows potential uses for the purposes of constructing and amending earth structures for different projects, for the rehabilitations and closure of disposal site or utilizations, and it can replace the use of natural materials. So I think that I'm a bit long. Let me conclude. So I would like to thank my colleagues. This work was performed with the dedicated contribution of colleagues defined here, and also not only the colleagues from the laboratory, but from the Faculty of Chemistry and Chemical Technology from the University of Ljubljana. This work was carried out within the framework of different projects. And to conclude, I would like to thank you again for giving me an opportunity and for kind attention.
Yeah, thank you so much, Dr. Vesna. So excellent presentation. So a lot of fundamental work in terms of microcharacterization, mineralogical characterization. I see a lot of studies, on fly ash characterization and applications, but I haven't seen studies looking into a lot of these fundamental mechanisms based on this microcharacterization, mineralogical characterization, all the physicochemical changes that are happening in the material. So it's a very nice presentation. And so hopefully, attendees who are working